So this problem we're going to talk about polar. This is number 5 of the 2018 FRQ. This is a polar question. So what a polar question is the units are, it has to do with like turning around a circle rather than just x's and y's. So instead of x and y, the coordinates are actually r, being the radius, and theta, being the angle. So polar has to do with circles, essentially. So if I have a circle like this, okay, I should just redraw these. Oops. Delete. Okay. This is my circle. And inside the circle, we always have our triangle. So this distance from the center to the outside is r. This distance here is just our x value, and this height is our y value. And of course this angle is theta. So this triangle is how we relate our polar coordinate to our usual, like, just xy coordinate. So let me make that shorter. We have sine of theta. So remember sine, toa. That's how we remember how these angles relate to the trig functions. So sine is opposite times hypotenuse. Opposite over hypotenuse. So the opposite angle of that theta would be y, and then the hypotenuse is r. So sine is equal to y over r. Cosine of theta is ah, which is adjacent and hypotenuse. So cosine is x over y. And then tangent of theta is opposite over adjacent, so tangent is y over x. So with these little functions we have here, these little equations, we can relate theta with theta and r, which is part of our polar stuff, with our x's and y's, which is part of our what we usually do on the normal xy graph. So that's what polar is. Polar is just all about circles and angles. So let's look at the first question. I should write A. So we have graph of the curve r equals 4 and r equals 3 plus 2 cosine theta. And they intersect at where theta is equal to pi thirds and where theta is equal to 5 pi thirds. So that means this one right here is pi thirds, and this one right here is 5 pi thirds. And remember, theta is an angle, so that means this angle is pi thirds. Oops. And then this angle goes all the way around. This is 5 pi thirds. So, I kind of need to sneeze. Okay, anyways. Yeah, okay, I'm fine. So inside of this r equals 4 graph, we have r. So I'm pretty sure that's inside this graph. That's r. That's r. And also outside the graph of r equals 3 plus 2 cosine. Well, whatever. These two graphs make this shaded area. Okay. Write an expression involving an integral for area of r. Okay. So, I actually had to search this up. But the area of these little, like, the area of these slices of the circle I thought it was like an arc length, but I don't know, something area. It's equal to 1/2 r squared theta. So that's the area. You just have to know that, because yeah, maybe they'll put it. So you know how there's like an equation sheet in the beginning of the test. I don't know. Maybe it's on there. Maybe not. Probably not, since this is a more intricate formula to know. But if we want the integral of this, so that's why in the beginning of our integral we're gonna have a 1/2. And then r squared, we're going to have both of these squared, but we're going to have it subtracting from each other. So this one's the outside one, and then this one's the inside one here. So it's going to be the outside one minus the inside one. That'll give us this area. So we're going from pi thirds to 5 pi thirds. And then our two areas, and we want them squared. I mean, we want our two r's squared. So 4 squared and 3 plus 2 cosine theta squared. And then we want our d theta. So that's that part there. So what this area is this circle. Let me use a different color. And let me erase this. So it's this outside circle, and then we're subtracting this space from it. So that means we get rid of everything in here, and we're just left with r, which is what we want. So that's what this this area tells us, and that's what this integral is telling us. Okay, so they just wanted an expression, so that's literally it. So this first part was worth 3 points, which is interesting because it's a lot of points. So we get 1 point for having this constant and the bounds, and we get 2 points for the integral. Oh, I guess that makes sense. So 1 for that point, or like, I'll just write 2. So probably 1 for this part, and then 1 for this part. And then 1 for having that constant. So this constant comes from this area of a sector. Oh yeah, so apparently this is the area of a sector of a circle. That makes more sense actually. Okay. B. Oh, by the way, a sector of a circle is just a slice of the circle. So like that thing I drew earlier. The area of this is this. Okay. B. Find the slope of the tangent line of this at theta equals pi halves. Okay. So slope of tangent line has to do with x's and y's, but right now we're in polar coordinates, so we have r's and thetas. So how do we get from r's and thetas to x's and y's? Well, that's why we wrote these over here that related r's and thetas to x's and y's. So we want to isolate why did I write a y here? This is supposed to be r. Well, anyways. So we want to use these and isolate x and y. And the reason we only want to use sine and cosine and not tangent is because we only want one variable at a time. So if we use the sine one first, how do we get y by itself? Well, we just need to multiply this r back to the other side, and then that'll get y by itself. So that becomes r sine of theta equaling y. Actually, why don't I write this the other way around? Y equals r sine of theta. And then we just do the same thing to cosine, just put this one over here to get x by itself. So x equals r cosine of theta. And then we want the slope of the tangent line. So slope is dy dx. And to get to dy dx, we have to take the derivatives of this. But right now, they're all in terms of theta. So it becomes dy d theta and not dy dx. But remember, dy dx is equal to dy d theta over dx d theta. So if we find dy d theta and then we find dx d theta, we just put them on top of each other, and then that'll give us our dy d theta. I mean dy dx, which is our slope. So to take the derivative of this, we need to use the product rule. Remember, product rule is derivative of the first times the second plus the derivative of the second times the first. You just alternate which one is taking the derivative. So derivative of r is dr d theta times the second one. And then we're alternating. So now we're taking the derivative of sine, which is cosine. And we just have a tack an r onto there. So I'm just going to write the r first and then our cosine. And then we have dx d theta. So again, product rule, derivative of the first times the second plus derivative of the second times the first. I just write the r in front because that's generally how you write that. Okay, and now we're going to put them on top of each other. So dr d theta sine of theta plus r cosine theta over dr d theta cosine theta plus r sine of theta. Okay, now what we're missing, because we do have our theta, but we need to replace dr d theta with something. But they give us r, which is 3 plus 2 cosine theta. So r equals 3 plus 2 cosine theta. So dr d theta is just the derivative of this, which is negative 2 cosine theta. So the 2 stays because it's a constant, and derivative of cosine theta is negative sine theta. I don't know why I write cosine. Negative sine theta. Okay. So now we're going to put dr d theta where we have dr d theta, and we're going to put a cosine, we're going to put a pi halves where the theta is. And remember your notation. You put that line and then you draw your theta. Theta of pi halves. So now we're just going to put pi halves and negative 2 sine theta everywhere. So negative 2 sine pi halves sine pi halves plus, and our r, I forgot to solve for that part. Okay. So our r is equal to 3 plus 2 cosine theta. So if we plug in if we plug in a pi halves, so this is our r. If we plug in a pi halves right there, we'll get our r. So r is equal to 3 plus 2 cosine pi halves, which is cosine of pi halves that's right here on the unit circle, and that is 0, 1. And cosine is the x value, so cosine of pi halves is 0. So 2 times 0, this is 0. So we just have a 3. So that means our r is equal to 3. Okay. So now we can put the r, the 3 here. 3 cosine pi halves all over -2, another dr d theta, and then we're going to plug in the theta at the same time. And then our cosine pi halves plus 3 sine pi halves. So that is our slope. Okay. Now, technically, you don't have to simplify that because that is the answer. But if you simplify it, then it becomes 2/3. Okay, so I'm pretty sure you get the point either way if you don't write it in a sentence, because writing all of this into a sentence would be really annoying. Because it just asks you to find the slope, and that's the slope, so I'm pretty sure you get all the points either way. I'm going to move this. Oh, shoot, just took the entire thing. Move this over here. It's kind of messy, but... So this one's worth 3 points. We get 1 point for our dy d theta or dx d theta. So you can get that singular point by writing either one of them. But you have to have both, so... And then you get another point for having the dy dx equaling this thing. And your final point from the answer. So, yeah, you don't have to write it in a sentence. So, this would be fine. Okay, and now our last part. So, this was 6 points total. So we know our last part is also going to be 3 points, because each FRQ is worth 9 points. Okay, C. So it's moving along a portion of the curve of this one. Because remember, that curve is the 3 plus 2 cosine theta. It's going from 0 to pi halves. And the distance between the particle and the origin increases at a constant rate. So this is a related rate question. Okay, so the distance between the particle and the origin... wow, that was really ugly, but... The distance between the particle and the origin is the radius, because the particle is on the curve. So if I had a circle, and this was my center, and my particle was moving along this curve, then the distance between here and that particle, I should use a different color. The distance between that center and that particle is your radius of that circle. And it's telling us the distance is changing increasing at a rate of 3 units per second. So we know that dr dt is equal to 3 units per second, because the radius is changing at a rate with respect to time at a rate of 3 units per second. And then we want to find the rate at which the angle changes with respect to time. So now that's d theta dt, because it's with respect to time, rate of change of the angle. So this is a question mark right now. And where it changes, the rate of change at theta pi equaling pi halves. Okay, so this question can be kind of confusing, so we're going to go through this very slowly. So, we know we want to get to d theta dt. But we only have dr dt right now, and r. So we want to somehow connect dr dt to d theta dt. And if we take the derivative of r, we get dr d theta. So this is kind of like a -2 sine theta. So I just took the derivative of that. So this is kind of a bridge between the two, because the difference between this and this is that dr does not have a theta measure, a unit of measure in it, but this one does have a theta measure. Okay, so how we're going to connect the two is we're going to rewrite this to somehow cancel out the we're going to write this, no, we're going to write this one. Yeah, we're going to write this one times, well, how should I explain this? We want to go from here to relate these two. So how do we relate these two using this? So we have dr dt. This is equal to if we had dr d theta times something times d theta dt. And the reason this works is because this theta can cancel out with this theta, and then you're just left with dr dt. Oops. Which is what we have right there. Yeah, so that's how we relate the two. But I don't want to cross those out right now. Yeah. Yes, this is good. Because now we have this, this, and this all in one equation, relating them all to each other. Yeah. Okay, that makes sense now. I was just trying to think of how to put them together. So, yeah, we multiply these two together because then these thetas can cancel out. And then we're left with the dr and the dt, which is this. Yes. So that's how we related those together, and that's why we put them in that order. Okay, now we have... Actually, I need to move these up. I'm going to run out of room. Okay, now we can replace this dr d theta with -2 sine theta. And we're just going to keep the times d theta, because we want to know what d theta is. So d theta can also be rewritten as, if we move this to the other side, then we would get d theta by itself. So I'm actually going to rewrite this. So we're going to write this as d theta dt is equal to dr dt divided by dr d theta. So what we did is we divided this into this side. So then it becomes dr dt over this dr d theta. And then we had, what did we say dr d theta was? Oops. It was -2 sine theta. Okay. And then remember our dr dt was 3 from there, because that was the one they told us, the rate of 3 units per second. So we're going to put a 3 there. Okay, and then moving over, because I'm running out of room. Now we want to insert, why did I write d theta d theta? This is d theta dt. Okay, then moving over, we want to insert this theta equaling pi thirds here. So remember that bar, this bar is the way we notate that. And then we're just plugging in a pi thirds. So -2 sine of pi thirds. So sine of pi thirds, okay, so the way I remember this is that your sine and cosine values are either going to be, well, excluding pi fourths, your sine and cosine values are either 1/2 or 2 over square root of 3 over 2. Square root of 3 over 2. Yeah. So the way I remember is, I only remember that sine of pi 6 is equal to 1/2. And then from this, I know all the other ones. So how I know all the other ones is that it alternates what value is what. So I have sine of pi 6, so then I know sine of pi thirds is square root of 3 over 2. So if it's not this value, it's going to be this value. And this works if you change to cosine of the same angle as well. So if I know sine of pi 6 is 1/2, then I know cosine of pi 6 has to be the other value, which is square root of 3 over 2. And then you can even apply this one, the alternating, to cosine of pi thirds. So if I know cosine of pi 6 is square root of 3 over 2, then cosine of pi thirds must be the 1/2 value. So they just alternate. So I just memorize this one right here. And then from that I know what the other ones are based off of the alternating thing. And then you just have to memorize that sine and cosine of pi fourths is 1 over square root of 2. That's just one you have to memorize. So sine of pi thirds is square root of 3 over 2. But these 2's cancel out. So we have 3 over negative square root of 3. And if we rationalize it by multiplying both by square root of 3, then we get negative square root of 3 times square root of 3 is 3. And on the top we get 3 square root of 3. So here, I'll just write it out. 3 square root of 3 over negative 3. And these 3's cancel out, so we actually just end up with negative square root of 3. And the units are radians, because now whenever we work with angles, we work in 8 radians, not degrees. Anything with like a pi over 3 or like a pi over 6, that's all in terms of radians. Degrees would be like calling this 60 degrees, you know. So we work in radians. The pi's are radians. But it's with change to time, and time is in seconds. So this is actually radians per second. And then this is our answer. So the rate of change with respect to time, I could write it out in a sentence saying the rate at which the angle changes with respect to time and at theta equals pi halves. Wait, pi thirds, not pi halves. Is negative 3 radians per second. So this one was worth 3 points. We get 1 point for saying dr dt is equal to dr d theta over d theta dt. And we get 1 point for moving the r dr d theta over and getting this. So that's 1 point. And then we get our final point for the answer with the units. Honestly, you didn't even need to write a sentence for it, but it's always a good habit to write the sentence because then it makes sure that you absolutely do get the point. So that's polar.